18.1 is going to be done in 2 different videos due to the complexity and the length of 18.1. 18.1 is about the calculations with acids and bases. This first video is looking specifically at the ionization of water, or what's called KW. So ionization of water. The majority of acid-base reactions involve ionization within an aqueous solution. Being in an aqueous solution, that means those acids and bases are in water. Due to those interactions, water can also ionize as well. That can be represented by the reaction H2O breaks down into H plus and OH minus. However, this reaction favors the reactants, and it's an endothermic reaction. So that arrow is favoring water over the ionized version. Therefore, we can create its own calculation. Looking at the equilibrium, because it is an equilibrium expression, Kc is set to the products H plus times OH minus over water. Because this favors reactants, we expect a very small Kc value. Therefore, we assume the concentration of the measurable water at the initial stays constant at the equilibrium as well. Therefore, we want to isolate the hydrogen ions and hydroxide ions. So we manipulate the reaction, and we get this Kc times water. Because we're looking at the ionization of water, Kw becomes the constant in which we use in place of Kc, and Kw equals the hydrogen ions times the hydroxide ions. All right, so at equilibrium, Kw equals the hydrogen ions times hydroxide ions. Because it's a K constant, it is temperature dependent. And at 25 degrees Celsius, the Kw value, or the concentration of water, is 1.00 times 10 to the negative 14. By looking at pure water, we can now say why we say water has a pH of 7. Because it's pure water and there's nothing else there to interact with it, the amount of acid and base ions must equal. Therefore, the Kw is essentially hydrogen squared, which is what the pH measures. Just simply inputting and doing the math, we input the 1.00 times 10 to the negative 14 equals H plus squared. Take the square root of that, and you get 1.00 times 10 to the negative 7 equals your hydrogen ions. What's nice is when you have this 1.00, you can ignore that number, because even if you do put it into the calculation in which we had talked about in 8.4, the negative log of that value, you'll still get the same number, because 1.00 is essentially 0. And the exponent is the only thing that matters. Therefore, the pH is 7. If 1.00 was a different number, you'd have to plug that into this calculation in order to determine the pH. So Kw is temp dependent because it is a K constant, as we have seen every time we've used it. Keep in mind, the forward reaction is endothermic for water. When we change the Kw, that changes the concentration of your hydrogen and hydroxide ions, and therefore changes the pH. Here are some examples. At 0 degrees Celsius, we have a Kw value of 1.5 times 10 to the negative 15th. This would have to be given to you. There's no other way to know it, because the real value of 1.00 times 10 to the negative 14th, that is provided for you in your data booklet in Table 2, but that's the only value that is provided for you. Because, seeing in the previous slide, that essentially we get h squared, by taking the square root of that value, you get 3.9 times 10 to the negative 8. And that gives you your hydrogen concentrations. It's not a pretty number. So now we need to plug that number into the negative log. So negative log of 3.9 times 10 to the negative 8 gives you your pH of 7.41. We do this for 20 degrees, and we get 7.09. 50 degrees Celsius, 6.63. So we can see that as temperature changes, we have a change in the value of our pH. And we could predict it that it would have gone in this direction because it is an endothermic reaction forward direction. So as you increase temperature, you favor endothermic, which means you favor more products. You have a smaller Kw value, which means you have more hydrogen ions. Now the one major thing to take away from this is no matter the value, these are all the neutral points for the reaction which you're going to run, which is why it's essential to know what temperature you're running a neutralization reaction in, is so you know where your neutral point actually lies for that day based off that temperature. So looking at an example, if you have 1.00 times 10 to the negative 4 as your Kw, and we know a hydrogen concentration of 4.60 times 10 to the negative 8th, we can figure out our hydroxide concentration by doing simple math. So divide the two values and you do get 2.17 times 10 to the negative 7th. Now you can do some comparisons here. Looking at the values present, we have 10 to the negative 7th and 10 to the negative 8th. That means you can actually figure out if this is a slightly acidic, neutral, or basic solution we're working with. The values are different, so it cannot be neutral. Our OH is actually a much larger value than our H+. Therefore, we are working with a basic solution. Now, how do you actually determine the pHs of these? You can plug these in to your calculator. Therefore, you can calculate your pH given these values. So if pH equals negative log of your hydrogen concentration, take that, negative log of 4.60 times 10 to the negative 8th into your calculator, and you will get 7.32, roughly. You can also find your POH, which is the negative log of your hydroxide, and when you do that in your calculator as well, you'll get 6.66, roughly. Add the two together and you get 13.98, which rounds up to 14.0, which is what you should get either way. So therefore, your concentration of your hydrogen compound or ions are inversely proportional to your hydroxide concentration as well. If you increase one, you decrease the other. So if you increase your hydrogen ions, you decrease your hydroxide ions, and that is going to decrease the pH due to the increase of your hydrogen concentrations. So pH is inversely related to hydrogen ion concentration, and OH is inversely related to the hydrogen ion concentration as well. Now those values are not very pretty to look at. So we have Kw, which is an exponent number that we don't like to work with. We have our concentrations of hydrogen and hydroxide ions that we don't like to work with because they're nasty numbers. Therefore, we can manipulate this to show that if we take 10 to the negative 14, which is what Kw stands for, we then take 10 to the negative pH times 10 to the negative POH. We now get 14 is equal to your pH and POH at 25 degrees Celsius. And that is a much more simplified number, especially since we can directly measure pH with the other pH paper or pH probes and find the difference with our POH present. That being said, let's do an example of what all this could look like. So lemon juice has a pH of 2.90 at 25 degrees Celsius. Calculate your hydrogen concentration, hydroxide concentration, and POH. And it doesn't really matter the order. All right. So if we know our pH, we are looking for the concentration of our hydrogen ions. The calculation which we want to use, as we saw in 8.4, is 10 to the negative pH, since pH is what we know. Therefore, we're going to take 10 to the negative 2.90, and we are going to get 1.26 times 10 to the negative 3 moles per decimeter cubed. Do not forget your units as you are working with concentration. So we have that. You could also calculate your pOH rather easily, as 14 equals pH plus pOH, since we're working at 25 degrees Celsius. We know our pH is 2.90, therefore we can solve for our pOH, which we calculate as 11.10. That does not need any units, as it's just a representative value. Lastly, we have our concentration of hydroxides. We can do this one of two ways. Since we are looking for the concentration of our hydroxide ions, and we have just calculated the pOH, we can take 10 to the negative pOH, substitute the number in, calculate, and you get 7.94 times 10 to the negative 12 moles per decimeter cubed. The other way in which you could have done this is we know our Kw, we know our hydrogen concentration, therefore we could calculate our hydroxide concentration. When you go through and solve this problem of 1.00 times 10 to the negative 14th divided by 1.26 times 10 to the negative 3rd, you are going to get the same value. Pick a method that works for you, that you can remember, but there are multiple ways in which to solve one problem.